So today we're going to be making a PCA plot in RStudio. So I have some data I got from Kaggle, and it's about genres in Spotify. So it has these really interesting numerical features like tempo, liveliness, amount of instrumental, and I think what's cool is that there's these 8 different genres. So I'm curious if these 43,000 songs will cluster on the first few PCs based on genre when we use these numerical features here. So there's only about 13 features. When you use PCA, you often have several hundred or thousands of features. And I'm just going to start small for the purposes of this tutorial. So I have the data stored in one of my local directories, and I'm going to use a function, data table, to format my data. So the data table will give me fread, and fread is a nice function you can use in R and several other platforms that allows you to quickly upload data. So we'll go ahead and do that. Okay, so just to get a look of what the data looks like, here are the dimensions of the data. So it's about 42,000 rows, 22 features. Okay, so let's just convert this to a data frame. And then I'm going to grab the features that I've pre-selected that are numerical. So okay, so now there's this handy function in R. There's actually a couple of different options you have. I'm going to be using one called prcomp, and this is actually in base R stats. And it's pretty straightforward. All you really need is the data, and one important thing is you want your data to be on the same scale and centered. So I'm going to make sure I have that set as a parameter. So scale equals true. Okay, and so the result you get, there's several different values, and the one we're interested in, the one that you'll see in a lot of papers when people plot PCs, is this. So this is the PC scores. So if you check the dimensions, that will be helpful. You'll see it's this is the number of samples, 42,000, and then this is the number of features. Well, this is actually the number of PCs they calculate. So the way PCA works, it will calculate up to the number of features you have. So yeah, we'll have 13 PCs. So just to take a look at what this looks like. Here's the first 4 PCs, and then these are the PC scores for each of the samples. So also when I plot this, I want to get the labels I'm using. So I'm going to pull the genres. Okay, and then I have this function I wrote in R, so you'll be able to get this later. But this is a little function I wrote for plotting in R. So take your output from PCA, the labeling you want to use, and then the title of your plot, and then what PCs you want to plot on the first axis and the second axis. But just to go into line by line what's happening here. So we have our output. So let's call it out And then I'm gonna make this a data frame. Okay, and then it has some grouping. In this case, it's the genres. Okay, and then I'm gonna define. So say I want to plot the first two PCs, right? So I'm just gonna make it easy for myself later on. Call that one plot X. If out 1, plot Y, if out 2. So that's PC1 and PC2. Okay, so I'm going to be using ggplots. So make sure you load plot 2. Okay, then I'm going to plot. So color by the groups. Okay, and also add some title, so genres. Okay, this is going to be a scatter plot, right? So G on point. You often want a white background, so theme BW. And then I'm going to add some labels. Xlab 1, 2, and then okay. So this takes some time. It's 42,000 points. Here we are. So it's a lot of genres, but it's interesting. So you do see these points are clustering based on genre. So it's a lot of different categories. You'll see there's some bias in what genres are represented here. But yeah, and so it's kind of interesting, right? So we see PC1 and PC2 might be informative. And one thing a lot of people are interested in is how many PCs do you actually want to look at? And is there more a more quantitative way to determine that? And one way to do that is the eigenvalues. So the eigenvalues represent, so one way to represent the contribution of each of these PCs to the total variance in the data. So in your, going back to this PCA result, so that had a lot of different things. This is the standard deviation of the PCs. So we're going to use this to calculate the variance of the PCs. And this will be proportional to the eigenvalues. So PCA result is dev 2 to the second power, because that's variance. And then say we want to convert these, so these eigenvalues, this is what they look like. There's one for each of the 13 PCs. And you'll see there's some eigenvalues that are much higher than the others. So it looks to me like these first 4 PCs are really informative for the variance in the data. So let's take the proportion of these eigenvalues. Okay, let's plot. So this isn't any fancy plot, it's just a regular plot, but you'll see here that the first PC represents about 20% of variance in the data, and then it slowly dwindles down. So it means that these later PCs are not as informative. Now, one easy way to do this, now that you know how to calculate your own values, eigenvalues, there's actually a a package that can do this for you. It's called Facto Extra. So you can install this, and you can easily visualize eigenvalues. So basically gives us what we just did. So you'll see these are the same numbers, just plotted a little better. And so maybe one thing you want to look at, this is called a scree plot, is maybe the elbow in the data. So the variance explained by the PCs quickly drops off after, I don't know, like 5 PCs. So maybe you're only interested in the first 5 PCs. This can be helpful. Maybe you want to look at the first 5 PCs. So using this function I made, it easily plots the PC plots for all the PCs you're interested in. So PCA, so PCA result X is what we're plotting. Genres. Okay, so let's say we want to plot PCs 5, 4, and 6. Okay. Okay, so 3 and 4 maybe not so informative. Let's look at 5. Okay, so there's something interesting going on here, right? Maybe this is related to some other data in our data set that we haven't looked at. It could be any of the other categories, right? I'm kind of curious to see how does the data look with fewer groups. You know, sometimes if you have too many groups, you don't see any clear patterns. So I picked out these 3 genres, which are actually pretty different. And if you just want to look at, you know, what are the different genres we have, you can do table. So we have R&B, psytrance, hip-hop. So I was thinking, okay, techno and hip-hop, they kind of seem pretty different. So I'm going to take a sampling. So sampling. So we have this genres vector we drew earlier. Okay, I'm just going to take the ones that are in my select genres. Okay. Sample. Class sampling. Okay. Again. Features. True. Okay. So what does this look like? Let's just make sure. Okay, so these are, we have 10,000 samples, 13 features, as you know. And then if you're curious, you may also want to look at the loadings. So in this case, the loadings is called rotation. So the loadings represent basically what is the linear combination of features that defines each PC. So if we look at maybe the first 4 columns and rows, you can get a sense of this. Okay, so danceability, energy, key, loudness, right? How does each of these explain PC1? So this is like a coefficient. You can think of like a linear model of all these variables that produces the calculation for PC1. So let's actually take a look at this more closely. So let's look at PC1 and let's sort. Okay, so you can see PC1 mostly explained by instrumentalists and then the duration of the song, and then lastly by energy. So we haven't looked at what the PCA plot looks like yet. Let's take a look. Genres. Okay, one. I'm just going to look at PC1 and 2 for now. Alright, so this is interesting. We have hip-hop on the left, techno on the right, and then it looks like dark trap is somewhere in between. I did not expect that. And so now that we've seen how this PC looks like, so PC1, it seems to represent a lot of like the instrumentalists and the duration of the song. So that's really interesting. Okay, so one thing I want to note, once you have your your PCA plot. Okay, so say you want to plot just PC1 and PC2 here, and then so now you want to save the plot. So you can do that using ggsave. You'll provide your plot, p file name. I'm gonna save it to my input directory. So data dir. Okay. Then PC1 and 2. Device PDF. Right, so this is a list. Okay, so now if I go there, you'll see it is saved here. So I just wanted to also talk about some of the alternatives to prcomp. There's a lot of different options out there. So another one is you've heard of it, so prcomp. And so it's a lot of the same input parameters, data. The output of prcomp is actually very similar. So if we take prcomp results, simple. So it looks like it doesn't do centering and scaling for you. So just to be safe, you may want to center and scale beforehand prior to putting it into prcomp. And then just to look at how does the output of prcomp look. So instead of rotation, like it is in prcomp, it's called loadings. And then you have the scores are just called scores. So that's your PC scores. And then SDev is the same. Yeah, so that's pretty similar. And then a last option, when your data gets really big, both of these functions can take an extremely long time. So say you have like samples on the order of tens of thousands, features also on that order. That's where you may want to use something a little faster. So when we looked at the discrete plot a while back, so we saw maybe like the first 5 PCs are all we're interested in. So that's actually convenient. We can use a package called bigstatsr. Bigstatsr. Okay. One thing when you use bigstatsr is that you want to first convert it to a format called FBM. So we have our numerical features. We want to specify the type of data we have. And then we're going to do SVD, because SVD and PCA are highly related. So we're interested in the first 5 PCs, so that's what we'll specify. And then we want to use centering and scaling, right? So you're going to specify scaling function. We're going to use big scale. That's going to be faster for a big data set. Equals true, scale equals true. That will give us what we need. So here we go. Okay, it's very fast. And you'll see when you get really large data sets, it's going to make a big difference. Here, it's not really going to make a big difference. In order to get the PC scores, what you want to do is you want to multiply the left singular vectors by the diagonal of the SVD value. So let's just look at what the help page says. So it decomposes the matrix into U times D times V transpose. So if you multiply the U matrix by the singular values, you get the PC scores, which are going to be equivalent to what you saw earlier. So what did we see earlier? We saw, so let's run PCA one more time on the numerical features, right? Okay, so PCA result X looks like this. Then PC score calculated from big SPD looks exactly the same. So that's really nice. And the reason is that it's fast. There's a random aspect to it, but when you know exactly how many PCs you want to calculate, it's actually really convenient. So this is a handy thing to use with big data. Yeah, so that concludes the video. And I'll post the code up on the GitHub page that will be linked below this video. Alright, thanks for listening.